has been aimed on understanding the impact of oil and gas on ecosystem dynamics in the Gulf of Mexico for more than 20 years. And before the oil spill, we had a long-term observatory site at Mississippi Canyon, and Site 118. And we had a lot of background data for the Mississippi Canyon area, and there was actually a research expedition out on the water when the Macondo well blew up. So, for me, as somebody who really fell in love with deep sea oceanography and extreme environments and oil and gas seeps, working in the Gulf of Mexico, when the oil spill happened, it wasn't just an oil spill. It was a sort of a disaster in your best friend's backyard. And I felt like we had to do whatever we could do to try and figure out what was happening to the system. So our approach was to document impacts in the water column, the sediments, and try to understand how the changes that we were seeing compared to the dynamics that we see at natural hydrocarbon seeps, because they are really fertile learning grounds for understanding the biological, chemical, and even physical processes that distribute oil in the environment and impact microbiology and higher animals' well-being. So the main things that we focused on initially were tracking the fate of hydrocarbons, like where did the oil go, where did the gas go, how did it impact different parts of the system. So we first started with a group that was working mainly on the water column and looking at oil snow sedimentation with Uda Passau and Vernon Asper and Arna Dix leading that part of the charge, and Joe Montoya and myself and Ajit Subramanian and Jeff Chanton looking at the fate of the petrocarbon in the system. And then we teamed up with Chuck Fisher and Liliana Bombs and Eric Cortez when ECOGIG sort of came together about 2011 or thereabouts, and Ian McDonald for the remote sensing to really get sort of the bottom effects, the remote sensing, looking at natural distributions of oil, trying to figure out, from the remote sensing data that was collected during the oil spill, how much oil came out, where did it all go, those sorts of questions. And surprisingly, 8 years later, we've learned a lot. We know that every part of the system that we've studied, from microorganisms to phytoplankton and zooplankton, everything responded at a different time scale. And that was surprising to me. Particles responded at a different time scale than the biological or the living organisms. The deepwater corals, super slow response, and are still being acutely impacted by the oil spill. So we're sort of in the chronic phase of impact now, but the impacts are acute, like limbs fall off, branches fall off the corals. Still, 8 years later, and that's really surprising. So I think that, it's a pity this isn't a 20-year program, because I think we have 20 years worth of work that could be done to really document all of the impacts properly. But we've learned a tremendous amount in these 8 years. Three things sort of stand out to me. One is when you think about this oil sedimentation event, I think in the beginning, a lot of people, including a lot of people on our project, thought that this, the oil was in the system, and then some of it sedimented out of the system. And it was surprising when we started looking at time series data, because it actually required quite a bit of time for that signal to completely attenuate out of the system. We were getting super oily material in the traps for about 10 months, 11 months. And the particles are still, 5 years after, the particles were still enriched. So when you filter water and look at the particulates, you can still see a signal from the Deepwater Horizon. So the longevity of the impact in the water column, I think, surprised a lot of people, surprised me, because when you talk about ecosystem resilience, everybody's, the Gulf of Mexico has rebounded, it's fine, everything's back to normal, but it's not. It's the stuff that you can't see that's still going back to the baseline. Another thing that was quite surprising was how long it took the microbial populations to sort of drop down to their baseline levels of activity. And from the rate measurements that we made, looking at things like methane oxidation, we saw that methane oxidation was elevated for 3 years after the event. So the gas input shut off, but methane oxidation stayed high for 3 years. That's unexpected and very surprising. And we still don't know why exactly it lasted for that long. But I think you had this huge population that grew in, and then it's essentially the attenuation of that population in the system, so the loss of all that biomass. But that's really surprising because these are organisms that, they don't live for years. They live for days. So the fact that you see a signal for 3 years means that something really interesting is going on that we need to understand. So in terms of general Gulf ecology and application to broader ecosystems, I think the most important, we've done a lot of just basic ecological work and sort of, I call it the biogeochemical, physical plumbing of the system, how the system actually works. And one of the most surprising things to me was that, how does a natural seep impact an ecosystem? And that's a question that we've been pondering for quite some time, but we've been focusing on the bottom, the area right around the natural seep, because you get chemosynthetic animals, mussels and tube worms, and you get all kinds of associated fauna that come in to the seep and feed off the organisms in the seep. So I think a lot of people sort of assumed and considered this seep impact to be very localized around the bottom. Well, what we found that was surprising was that seeps actually impact the surface water. They impact the whole water column, and they influence even the phytoplankton productivity at the surface. And that was a shock to me, a real shock, because in 1,000 meters of water, that shouldn't happen. I mean, everybody thinks of the ocean as a top-down system. Primary production happens at the top, detritus rains down to the bottom. And yes, there's upwelling, but this isn't the classic upwelling that happens along the western margin or because of an eddy. This is upwelling because of hydrocarbon seepage. But it's upwelling that's fundamentally important in terms of how the system works, because think of how many hydrocarbon seeps there are in the Gulf of Mexico. But one of the real sort of nuts and bolts part of this is, how does the microbial community of oil-degrading bacteria respond to a huge pulsed input of hydrocarbons? What's their capacity? How much can they oxidize a day? It's sort of like how much chocolate can you eat in a day without getting sick? I like that analogy a lot, because these organisms, they can eat, they're pretty good at turning over hydrocarbons, but they have limits. So there's only so much they can do. So I really don't know that we have a full answer to that question yet, but we've made a lot of progress. And that's critically important, not just for big spills, but for small spills, because if you've got, what size of a spill requires a huge response? Like it's how many barrels of oil can the community metabolize effectively without you having to go out there and start doing all kinds of booming and burning and dispersant application, et cetera. And that's a fundamentally important question, because it's a smart response to let the environment handle it as long as it's not going to harm the environment. And we need to know what that threshold is for environmental harm. Like, how much can they take before we need to give them some help? And that's something that we're closer to answering that question than we were 6 years ago. I don't know that there's a single solution, but I think that there are consistent sets of environmental parameters that call for a specific solution. So if you have condition A, B, C, and D, you do this. If you have E, F, and G, you do that. If you have K, L, M, you do that. And that's what we need to figure out. What are these combinations of environmental conditions, both physical, chemical, and biological, that set up a system to be successful or to fail with respect to oil exposure? And if we can figure out what makes an environment more capable of handling oil exposure, then we can figure out how to do a smarter response.